可以了。
Okay. Yeah, I think it works perfectly.
Okay.
Are you in New York now?
Yeah, in my office right now.
Oh, your office. But did you also move to New York? I mean, your apartment.
Yeah, I live in the city.
Okay.
My apartment is 5 minutes walking from my office.
Oh, 5 minutes walking. Wow. Nice. Okay.
So how's everything in Fudan? Everything is normal, or is it also a pandemic mode?
Yeah, it's some kind of under control.
There was some minor outbreak in Shanghai.
Yes. There are like 3 positive cases.
Yeah, that's nothing compared to what's happening in New York.
Right. But already, you know, the local government is very serious, nervous, you know.
Yeah, I can imagine. Yeah.
But in the US, I guess the domestic conference, the workshop, all of them goes to the normal case.
Yeah, everything is happening, mostly happening in person.
Okay.
Yeah. But it may become it's more difficult for your people from Europe to attend some of the in-person meetings. Yeah, because there were some travel restrictions.
Yeah, I heard that Japan is already, you know, closed the country.
Yeah, once again.
Yeah, let's maybe wait till 1 more minute, then we can start.
Sure. So is this like a usual seminar time, or this is only like for because of the
this is for the US speakers.
I see.
We
Because,
have no choice.
It's rather early for you too.
That's right. Yeah, it's not that early, but it's relatively okay. It's 9 a.m.
Yeah, but for people, I guess for like people who commute, this is very early, right?
Yes. Yes.
Hey, 怎么了？
不是说要 meeting 吗？
我 listen，我就 listen，我不需要 meeting。
Or maybe I have the duty to mute in case there's noise. What should I
Okay,
do?
we haven't started yet.
Yeah.
Sorry, I muted myself.
Muting. Okay.
Theory, finite volume. And then there's a whole discussion about symmetries, and you never have to address the question of whether it's spontaneous.
I heard Nati.
I think someone is watching YouTube.
Oh, okay. So Nati was joining through YouTube.
Yeah.
Okay.
Okay, I think we can start. Even though people are maybe still rushing in. Let's start. Today we are very happy to have Professor Yifan Wang from New York University. Actually, Yifan just joined New York University as a faculty member. Let me briefly introduce Yifan. Yifan is currently an assistant professor in the New York University. Previously, he obtained his PhD in MIT. His research focused on the non-perturbative aspects of quantum field theory and string theory, with applications to the strong coupled dynamics, both in high energy and condensed matter. So more recently, he's focusing is on the fundamental properties of boundaries or defects in quantum field theory. Yifan, please.
All right, thanks, Jan, for the very nice introduction. And it's my pleasure to visit Fudan again, this time virtually. I'll be talking about some recent work with Scott Collier, who's a postdoc at Princeton, and Dalimil Mazak, who's another postdoc at the Institute in Princeton. And this paper has been submitted and it will appear tomorrow night. So if you want to look into more details of what I will talk about today, you are very welcome to look at this paper tomorrow. So the title of the talk will be about bootstrapping boundaries and branes in conformal field theories. So let me introduce the main player. The main player today will be conformal boundaries of 2D CFTs. So this program I'll talk about, of course, can be pursued in higher dimensions, but to be concrete, we'll focus on two-dimensional conformal field theories in this talk. I should also emphasize that even though this is a Zoom talk, you should feel free to interrupt me if you have any questions or if anything is unclear at any point. I'm not sure if I will be able to monitor chat frequently, so if you have any questions or comments, please just speak up. Okay, so back to what I was talking about. I was just going to give you some brief motivation for the important role of boundaries, the important roles that the boundaries play in various contexts, in various branches of theoretical physics. For example, in condensed matter theory, this boundaries shows up as impurities in, say, one-dimensional quantum spin chains. And the famous example is of boundary effects that are important appears in the context of a Kondo effect, and this gives rise to the so-called Kondo problem that leads to strong coupled phenomena, interesting strong coupled phenomena that's finally resolved using various non-perturbative techniques in quantum field theory. The conformal boundary is also very important in the context of string theory. In that context, these conformal boundaries of the Walshy CFTs describe D-branes, which are important non-perturbative objects in string theory. And finally, more recently, via the ADA-CFT correspondence, conformal boundaries of large N 2D CFTs with holographic gules correspond to, in the bulk, to the so-called end of the world branes, which I'll abbreviate as ETW branes in the ADS3 quantum gravity. As you may imagine, because of this various manifestation of conformal boundaries in various corners of theoretical physics, there's a rich history in studying these objects. For example, there have been many examples of conformal boundaries in rational conformal field theories, some of which I'll review briefly. And in the context of string theory, some of the well-known boundaries, conformal boundaries of the Walshy CFTs describe supersymmetric or BPS branes in string theory, such as the familiar D branes in type 2A and type 2B string theory on flat space. And also more recently, there are various semi-classical descriptions of this end-of-world branes ADS3 just by studying the solution to the Einstein equation in the presence of a boundary that extends into the bulk. Just given this, these few bullet points, there are some immediate questions that one can raise. So already in the context of boundaries in rational conformal field theories, one can ask if there's a classification of the set of boundary conditions for rational theories where the entire local operator spectrum is known. So these boundaries should be thought of as the extension of the local operator algebra in this rational conformal field theories. A subset of them have been classified, but one can ask if there's a full classification of conformal boundaries in such solvable theories. It turns out this is a rather non-trivial question already in this context. And in the context of Branes in string theory, as I mentioned, there are these familiar examples that you learn from string theory 1 or string theory 2. There are these D-branes, supersymmetric D-branes in type 2A or type 3 string theory. But one can ask if there are other interesting, stable, non-PPS branes in this theory. And again, this is something that's not known. Okay, there are a few examples, but most of this is not explored as of yet. And lastly, I mentioned there are these semi-classical descriptions of the end of the world branes, ADS3. One can ask if these semi-classical solutions are truly valid at the quantum gravity level. Okay, so for example, one can ask if these solutions are consistent with the notion of pure gravity. Okay, including this branes. Okay, and this should be something that one can address at the level of the dual 2D CFT with boundaries. So what is the goal here of our work? The main goal is to explore the landscape of boundaries using the recently revolutionized technique of conformal bootstrap. Okay, the philosophy of this bootstrap is to explore rather basic consistency conditions of the underlying conformal field theory, but here the conformal field theory also are endowed with additional structures known as conformal boundaries. Okay? But it's a rather straightforward extension of the bootstrap philosophy that have been pursued extensively in the recent years. If one were to kind of explore or charter the landscape of some boundaries or boundaries in conformal field theories, one would like to first introduce some coordinates on this landscape, right? Before you put before you carve out the landscape, carve out a lot of regions. A natural set of coordinates for CFTs with boundaries are given by the following. Okay, so there's a natural notion of a gap for the bulk scalar spectrum. So you can think about as the spectrum of the CFT on the cylinder, where the spatial slice is a circle. And this delta determines the gap in this spectrum on the circle. And another important coordinate for CFTs, of course, is center charge, which is a kind of universal quantity that characterizes the degrees of freedom in your theory. And in the presence of boundary, there are analogous quantities that are equally important. One is the so-called boundary tension, and its logarithm is also what's known as the boundary entropy. This is the close analog of the bulk center charge in the sense that it characterized or it gave the measure of the degrees of freedom on the boundary. Okay, and something similar to the bulk scalar gap in the case of a boundary is the bulk boundary gap, which measures the gap in the boundary operator spectrum. So in other words, you can think about this as a gap for the CFT on the interval, where on the two ends of the interval you impose the boundary condition given by the conformal boundary of interest. And H gap measures the gap in the spectrum on this interval. So after presenting to you this general goal, let me just summarize some of the main results that we obtained in this paper. So in this paper, for simplicity, we focus on boundaries of bosonic conformal field theories. So one of the main results is that given this set of coordinates, we discover a universal bounds on these coordinates. Okay, so this is what I meant by carving out the landscape, allowed region in the landscape of CFTs with boundaries. Okay, so we're going to put bounds on these coordinates. So some of the bound we find is some kind of universal upper bound on the brane tension as a function of the bulk center charge. Okay, and this upper bounds applies to boundary conditions that are stable, meaning that the boundary operator spectrum has a gap that's above 1. Okay, in other words, there's no relevant operator on the boundary. Okay, and furthermore, we also find that in the sequence of RCFTs, with central charge bigger than 1, where there is not a classification of the conformal boundaries, we find unique solutions to the question about stable branes in such theories. Okay. And in the context of large N dualities, for example, regarding these semi-classical solutions that I mentioned in ADS3 that correspond to end of the world branes, we use our bounds at large C to derive implications for such semi-classical solutions. We find that these naive semi-classical solutions are actually incompatible with the strict notion of pure gravity in ADS3. And this will have interesting implications, which I'll mention in the later part of the talk. And finally, using numerical technology, we obtain various refined bounds that are not just upper bound, but also lower bounds on the brane tension. But now it would also involve a dependence not only on the bulk center charge, but also the bulk scalar gap. And relatively, we can also get some refined upper bound that now depend on the value of the boundary operator gap. In addition to the numerical bounds, I'll also explain that with some analytic tools we developed, it gave rise to exact, precise proof for the spectrum of branes in some rational theories, such as in the E level 1 CFT and the non-holomorphic monster CFT. We'll show that in these theories exactly this bound is satisfied exactly. Okay. So these are just some overview of some of the main results that we obtained in this paper. Any questions?
I have a question about point 3. So
yes.
by the semi-classic UW brane for the 3-dimensional pure gravity, I'm trying to understand that you assume even the 3D gravity is quantum gravity, but the brane is still classical, or that's what you mean?
No. So the question is the following. So you have some putative holographic dual. So you have some putative gravitational theory in the bulk with this end of world brane, and you want to ask if this solution is complete in the sense that there's a holographic dual CFT and some boundary in that theory that correspond to these objects. Okay.
Yeah, but
and the answer is that it's not always possible.
It's not but this,
so it will depend on the detail of the end of world brane. So the naive description of this end of world brane in the putative pure gravity, quantum gravity theory would not be consistent at the quantum level. There will be some non-trivial bound on what kind of end of world branes is consistent. Okay.
But do you also consider the theory on the brane world volume? Or?
So these are some particular end of the world brane. These are the simplest ones that Takanagi introduced. These are the ones that with constant energy density.
Yeah, it's just curious if whether this suggests you should consider some quantum theory on the brane world.
Yeah. So that will be one way out, for example. So the question here is that you have some candidates and you ask if they're consistent at quantum level. Of course, you can cook up many more other candidates and ask the same question. But here we're just going to address the simplest one.
Okay, thank you. Another small question is: you assume this box CFT is compact?
I will explain. Yes. The CFT is always compact. I will emphasize that. Yes.
Okay.
Yes. Thanks for the question. Okay. So let me explain the setup. So as Yang have anticipated, so here I'll focus on a CFT, particular kind of CFT that is it's unitary. Okay, so this we all know, but it also requires the 2D CFT to be compact, meaning that there's a discrete spectrum and there's a normalizable vacuum. So these are the properties that we like about CFTs. Okay. And also I'll focus on CFTs with center charge bigger than 1. And the reason is that for center charge smaller than 1, the conformal boundaries have already been completely classified. Okay. And so the spectrum of the CFT on the circle will be, as usual, will be labeled by dimension and the spin. And And compact just means that this energy spectrum is discrete. Okay, it's not continuous, and the spin is quantized as usual. And conformal boundaries in this case is also sometimes referred to as boundary states. As you will see, there are equivalent ways to describe the same object. Okay. So how do we see that? One way to describe a conformal boundary is to impose a boundary condition for your 2D CFT. So imagine that you have your quantum field theory, you have your conformal field theory living on the upper half plane, okay, parameterized by the complex coordinate z, and say the CFT lives on the upper half plane where the imaginary part is positive. Okay, a conformal boundary condition is a boundary condition you put on the real axis in this coordinates, and for the boundary condition to be conformal means that the stress tensor have to obey this condition, gluing condition, at along the real axis. Okay, and it should also remain traceless. And if this is true, then this boundary condition will preserve the diagonal conformal subgroup of the bulk conformal symmetry. This picture is equivalent by a conformal transformation to this picture, where the conformal boundary along the real axis is mapped to the boundary of a disk, to a circle. Okay, and it's in this picture that naturally the boundary condition has the interpretation as a boundary state in the radial quantization. Okay, and this is the reason why these two descriptions characterize the same objects, the conformal boundaries in 2D CFTs. Now, how do you characterize a boundary state in a concrete, in a given CFT in a concrete way? The way you do that is to use a very nice spaces. The spaces are so-called Ishibashi state. Okay, these are states in the Hilbert space in the radial quantization. So you think about this circle as the S1 that you quantize your theory on. This is a state in this Hilbert space. That's nice in the sense that it solves the conformal word entity required for a conformal boundary state. Okay, and then the non-trivial information that's not fixed by the word entity are these coefficients, which determine essentially the one-point function of the boundary in the presence of a bulk operator labeled by phi. Okay, and because of the symmetry of the problem, it turns out that only the scalar operators in the bulk carry a non-trivial coefficient. Okay. Out of this expansion of a boundary state into Ishibashi state, important part is the coefficient multiplying the Ishibashi state associated with the identity operator. And this is precisely the brane tension, which I introduced previously as an important part of the coordinates on the space of CFTs with boundaries. Okay, and log G is the so-called boundary entropy. So as I've mentioned already, writing your boundary state as a linear combination of Ishibashi states already take care of this word identity. But these coefficients are subject to, is there a question?
No, I don't think so.
Okay. Right. So this already take care of this word identity, but the coefficients are subject to further consistent conditions of the 2D CFT. It's an extension of the usual crossing and modular invariance of 2D CFT in the presence of a boundary. So these are a consistency of the so-called open-closed axioms of the CFT. So there are two such consistent conditions. The two such basic consistent conditions, and all the other consistent conditions are built out of these. One is the so-called Carty condition, which comes from looking at the cylinder Panin function of the 2D CFT with the boundary condition imposed at the given time and the later time. Okay, so these are the two boundary conditions imposed at the two ends of the cylinder. Now, if you think about this cylinder Panin function, there's two different ways to quantize the theory. So you can either quantize the theory by choosing this as the spatial circle, this as time, or you can look at this cylinder sideways and treat this direction as time and this direction as your space. Okay, and the two different ways to quantize the theory give you two different ways to decompose this cylinder Panin function And the consistency of the open-close CFT tells you they have to be the same. Okay. And another consistency conditions coming from the open-close axioms of 2D CFT is the so-called the bulk boundary bootstrap equation. It's also known as the Cardy-Levelin equation. This equation also, unlike this equation, the Cardy condition, which is genuine in 2D, this bulk boundary bootstrap equation generalized naturally to higher dimensions, as you will see, which is kind of obvious after I explain. The reason that this bootstrap equation just comes from looking at two-point function of two bulk operators in the presence of boundary. Now, there are two different OPE channels that you can consider in with such observable, namely two-point function of the bulk operator in the presence of boundary. One OPE channel involves taking the two bulk operators close to each other, in which case you decompose into other bulk local operators, which can develop a non-trivial one-point function with a boundary. So you sum over bulk OP channel on this side. But alternatively, you can also take the OP channel where the operator fuse with the boundary first, okay, and then exchange some boundary operators with the other bulk operator, which also fuse with the boundary. Okay, so this is the so-called boundary OP channel. And again, essentially the associativity of the CFT in the presence of a boundary ensures that these two sides have to be equal, okay? And this gives rise to this additional bootstrap equation. Just to emphasize, these two equations are in general, they give rise to independent constraints, okay? So one does not imply the other. Although in RCFTs, because of the strong constraints, because you have only a finite number of conformal blocks, and that give this condition already give very strong constraints, sometimes lead to unique solution. And in those cases, this equation can be satisfied in a miraculous way. Okay.
I think there's a question in the chat box.
Let's see.
Can you read it, or I can read it for you? Is this guaranteed that the Ishibashi state span the whole boundary state even in the C greater
That's
than
right.
1?
So the Ishibashi state give you the complete basis that solve this word identity. But of course, by here, when I talk about Ishibashi state, it could mean different things in the literature. But here by Ishibashi state, I mean the Ishibashi state for the Virasoro algebra. In literature, people also talk about the Ishibashi state for enhanced chiral algebras. And if you only focus on those Ishibashi states, which are special combinations of the Virasoro Ishibashi states, you're not going to span all the boundary states. But here, I'm really talking about the Ishibashi states just for the Virasoro algebra. Okay. Hope that addresses the question. Okay. So. Yeah. Okay, so I presented to you this general consistency conditions, and what is the general expectation? Okay, the general expectation, which is not proved at the mathematical level, but is kind of intuitive at the physical level, and it's true in various examples. That is, the set of conformal boundary states is completely fixed by these two conditions: the Cardy condition and the bulk boundary bootstrap equation. Okay, through the local CFT data. So if you know the bulk operator spectrum of your CFT and you know their OP coefficients, the set of conformal boundaries is completely fixed by solving the two equations. Okay, so on this side, you will have to consider equations with arbitrary bulk operators in principle. Okay, and as I said, this is true in all the examples we know. And I want to emphasize this is contrary to higher dimensions, where it's common to have theories with the same local operator spectrum, same OPE of local operators, but different boundary of different spectrum of boundaries, okay, and more general defects. But in 2D CFT, this appeared to be not the case.
Sorry, you said the previous two consistent conditions are independent, but
they're in general independent. One does not imply the other.
But maybe there also have some overlap, because in the textbook, people usually don't discuss the second one. But
that's right. That's a mistake. Yeah. So already in Ising CFT, you can easily convince yourself that you can find more solutions. In Ising CFT, you can find more solutions by studying this equation than those that you can find more solutions by studying these equations, and only a particular one of them is correct, and that one is picked out by studying these equations.
I see. You mean even for diagonal rational case, this?
Yeah, even for Ising CFT.
I see. Okay. Or maybe one more. So in higher dimensions, what is the first analog of the second considered condition? Some kind of.
This one?
Yeah. You mean yes. Yeah.
In higher dimension, this condition it just carries over. You just look at the boundary condition, on this D+1 dimensional submanifold, and again you consider a local operator OPE, right? And you have these two decompositions. On one side you have the bulk OPE channel, the other side you have the boundary OPE channel, and these two expansions should give the same answer. And that's the non-trivial constraint. And there have been some work to kind of elucidate this equation, but no attempt have been made to actually solve this equation in higher dimensions.
I see, but what about the first one in higher dimensions? I don't know.
Yeah, that's a very good question. I don't know the analog in higher dimension. Of course, you can consider something like a torus in higher dimension, but the connection to local operator spectrum is not clear anymore.
Okay, thank you.
Mm-hmm. Thanks for the question. All right. So I just for completeness, I explained to you the general setup and the most general constraint that one should study to fully characterize the space of conformal boundaries in 2D CFTs. But in this talk, in the rest of the talk, will be much less ambitious, and we're just going to start study constraints on this coefficients in front of Ishibashi state when you expand the conformal boundary states using the simplest condition. Well, one of the simplest condition, namely just the Carty condition, and with identical boundaries on the two ends. Okay, and the boundaries will be labeled by B alpha. Okay. And even with this very simple condition, it turns out that they will lead to very strong results, as I'll explain. And the magic, something you should keep at the back of your mind, the magic is coming from unitarity and positivity, okay? As is true for many results that we get from in quantum field theory, okay? Many of the non-trivial constraints are, the key to many of the strong constraints that we find in quantum field theory are coming from unitarity, or in other words, reflection positivity in the weak rotated Euclidean theory. Okay. Just to kind of eternalize the equation that we're going to focus on for the rest of the talk, the Carty condition can be written as follows. So here you have the you have the closed string channel closed string channel interpretation of the cylinder boundary function, which is the overlap between two boundary states. That's propagated by the closed channel or closed string Hamiltonian through a time parameterized by t, and the same quantity can be expanded open string channel, where it's going to be a thermal trace over the open string spectrum, with which is the spectrum on interval with boundary conditions specified by alpha B alpha. And the thermal trace is over a temperature that's given parameterized by this 2 pi over t. So it's like an inverse temperature compared to the left side, which is reminiscent of what you see in the modular for the modular invariance property of a torus boundary function. But here it's for the cylinder. Okay. And if you kind of unpack the both sides using the structure of the operator the structure of the states. The structure of the Hilbert space in the open string channel and the closed string channel, they can be packaged into characters. In this case, the Virasoro characters associated with scalar operators, okay, on one side, and then the Virasoro operators, Virasoro characters associated with the open string operators on the right-hand side, okay. The coefficient here involve this coefficients that we have seen that defines the boundary state, and on the right hand side, these coefficients are positive integers which characterize the degeneracies of this Virasoro primaries in the open string spectrum in parameterizing this Hilbert space. Those details are not so important. What's important here are, for the rest of the talk, are the fact that these coefficients are positive. Okay. This is the kind of manifestation of unitarity at the level of this equation. Is there a question? Okay. So let me make some comment. So this is this looks like a simple equation. So let me make some comments for why this is a non-trivial problem. Okay. So first of all, this may look simple, but it's actually a rather complicated equation. It's an equation that will depend on this parameter q or q twiddle, which are which are dual variables. Okay. That the parameterized in terms of the size of the cylinder, okay, which is the modulus of this manifold, space-time manifold cylinder. Okay, so it's going to be an equation that depends on this parameter. Okay, and this is reminiscent to the equation that Wang encountered when trying to attack the modular bootstrap problem, and for that reason, it's also sometimes known as the cylinder or annulus bootstrap equation. So even though this equation is complicated in the sense that it all depends on its parameter, and also that on the left and the right hand side, the sums are over an infinite set in general. Okay, it's because in general you have an infinite number of irresolvable primaries, unless you have standard charge smaller than 1. Okay, so it's an infinite sum. So it looks like a formidable task to solve this equation. Okay, but in RCFTs, if in rational conformal field theories, if this boundary state preserve a large chiral algebra, these equations can be solved exactly, okay? In which case, these boundary states are going to be in one-to-one correspondence with the chiral primaries for the VOA that defines the RCFT in the diagonal RCFT in particular. More generally, the boundary conditions for RCFT that preserve the chiral algebra will correspond to mathematically a modular category for the modular tensor category, which correspond to just the representation category of the VOA. Okay, this comment just for the expert. If you don't understand it, it's okay. Okay. And there is a way to, if you know some boundary state which solve this equation, there's a very nice way to generate more solutions with the following information given by the topological defect. So the idea is that if you have some boundary state which already solve these equations and actually which solve this equation as well, there's a way to generate additional boundaries that solve this equation by fusing a topological defect with this boundary state. Okay. And more generally, the space of these boundary states spanned over positive integers is going to be acted upon naturally by this topological defects, which defines a fusion category, which is a notion, which is a kind of a general notion of symmetry into these CFTs. And this kind of ring will be this lattice of these boundary states will become a natural module of this topological defects. There's a few remarks I want to make.
Is the finer action is similar to this usual simple current acting on the boundary state or something like that?
This will be a generalization of the simple current action. The simple current will correspond to the case where the topological defect is invertible. This notion I just mentioned would apply when the defect is not invertible. Yeah. Okay.
Yeah, and also the if you can also do a modular S transformation for the previous equation.
Which equation?
The previous slides. The consistent, yeah. The last equation, yeah. I mean, we know for diagonal rational CFT case, from this equation you get nothing but some kind of boundary or defect Wiener formula.
That's right. So for the
I was wondering which non-trivial constraint you can get in that case.
Oh, in that case, for the rational, if you're just studying the boundary conditions for rational CFT that preserve the chiral algebra, then this equation, as you said, is just trivially solved as a consequence of the Linde formula. physically it's because in that case, the infinite sums, even though they look infinite, they can be rewritten as a finite sum. And this just becomes a linear equation to solve once you use the S transform of the character. The non-triviality of this equation comes from the case when you consider more general conformal boundaries. Even in RCFTs, when the boundary does not preserve the chiral algebra, in that case, the sum are genuinely infinite. Okay, and then also the modular kernel for for the Rosara characters at central chart bigger than 1 is going to be it's not going to be a matrix anymore. It's the integration kernel, so the equation becomes much more complicated.
Okay, thank you.
Yeah. Okay. Yeah, so there were a few comments I wanted to make about this important coordinates that I introduced to label boundaries in conformal field theories. That is this G function. Okay. So this G function physically is important because it controls the high temperature behavior of the open string Branes function in the following sense. So if you look at the open string Branes function as a function of this temperature moduli, in a large temperature limit, the dominant behavior would have this exponential behavior reminiscent of the Cardi formula, where the coefficient will be determined by this G function of the boundary conditions. Okay. And if you're familiar with the entropic interpretation of the G function, you can also think about the G function as determining the thermal entropy, a universal subleading piece in the thermal entropy coming from the boundary. Okay. And this G function also gave rise to some regularized counting of the number of states in the open string spectrum. Okay. Which is again some consequence of modular S transform. And this is for this reason that this G has a similar it's similar to the bulk center charge in characterizing degrees freedom, now counting degrees freedom in the boundary operator spectrum. Okay. And another important thing I want to say about this G function is that they are monotonic under boundary RG flow. Namely, deformations of the boundary of the conformal field theory by operator that's localized on the boundary. Okay, we're labeled by psi here, and it's integrated along the boundary direction. And this generally triggers a flow between conformal boundaries in a given CFT. It does not change the critical behavior of the bulk theory, but interpolates between conformal boundaries of the same CFT. And the crucial feature of this G function in this context is that it gives rise to there's a natural extension of the G function to the entire flow given by the boundary entropy, which is monotonically interpolating between the boundary entropy of the UV and the IR of the boundary RG flow. Okay. And a particularly nice feature of this G function compared to other G or C or F or A function in higher dimension is that this RG flow is gradient. It's always gradient. Okay, this is not true even for C function in 2 dimension. And so the G has various nice features, as I mentioned, similar to the reminiscent of those of the bulk center charge, say the C anomaly in 2 dimensions. But there's one thing that's kind of unsatisfying. This is because for C, we know that unitarity puts strong constraint on C. For example, C has to be positive for interacting theory. So we can ask if there's some bounds on G. Okay, but it turns out that for a long time, people do not know if there are any bound on G at all. Apart from that, G has to be bigger than 0 for unitary theory. But log G, well, G can be anything that's close to 0 in particular. It was only until this paper that they would discover some weak lower bound with the assumption of some bulk scalar gap. Okay, and we'll see that this bound can be refined. Okay, in our work.
Can you explain a little bit more about the stability in terms of this boundary RG flow?
Right. So I skipped something. Yeah. So I skipped something because I saw that it's a 1 hour seminar, right?
Yeah.
I think I don't have 20 minutes left, so I skipped something. So here, by stability, I just mean that a stable boundary means that on the boundary there's no relevant deformations in this talk. So meaning that there's no operator of dimension on the boundary of dimension smaller than 1. If you do, you can consider this deformation, and this will trigger a boundary RG flow. And that's that's all I mean. Yeah.
Okay. But in the block, can you see the stability of the brane more intuitively in the block?
Well, the box CFT does not change. So
sorry, in the ADS block, the brane.
Oh, in the ADS block, right? In the ADS block, for the end of world brane, it will correspond to some shifting of the location of the end of world brane for the particular kind. But I don't know a general picture. Yeah, so in a ADS CFT, if you have a like Einstein gravity dual and the end of world brane is the one of the type which have a constant tension, constant energy density in the bulk, then the boundary entropy essentially determines how at what angle roughly the end of world brane anchors on the asymptotic boundary. Yeah. So a boundary RG flow in this case will correspond to changing the angle in the bulk.
Yeah, it looks to me that that condition you just explained is a little bit stronger, because even in the case of BPS case, say the brane is BPS brane, then you still demand and there's no relevant operator.
No, so this may be a small confusion. So there are different notions of stability. So here I'm using the notion of stability that's relevant in the most generic case. That is, it does not have a relevant operator in open spectrum. If you're talking about superstring theory, there you want to define stability in a different sense, because in superstring theory, the boundaries will always have to preserve into one supersymmetry. Okay, so there you want to consider branes that are stable against into one preserving deformations. That's a stronger requirement. So a brane may have a supersymmetry breaking relevant deformation, but may not have a supersymmetry preserving relevant deformation. Thus stable in superstring theory.
Okay, thank you.
So just to kind of make it clearer, so if you consider a so-called BPS string, BPS brane, is obviously stable against supersymmetric deformations that preserve the boundary into one supersymmetry, but in general, it's not stable against arbitrary supersymmetry breaking relevant deformations.
Okay.
Okay. Right. So this is a very long introduction, but finally we're ready to approach the Bootstrap equation. And the strategy to approach this complicated equation that involves infinite sum and also this one parameter will be through this so-called functional method, which was I think first introduced by Hellerman in the context of trying to solve the modular Bootstrap equation. Okay. So one start by kind of rewriting the Bootstrap equation as follows, which is essentially just gathering terms to one side of the equation. Okay. This is the contribution from the vacuum in the closed string channel. This is the term from the open string vacuum, and it's multiplied by 1 because in this talk I'll always focus on boundary conditions that are elementary. In other words, there's no dimension 0 boundary changing operator on the same boundary. Okay, so there's unique identity. And then you have the closed string characters and you have the open string characters. Okay. So how does the strategy work? The functional strategy work? Okay. So the idea is that you want to first fix the bulk center charge, and you put in some assumption for the bulk scalar gap and the boundary operator gap. So denote that such a gap by delta gap for the bulk scalar spectrum and H gap for the boundary operator spectrum. And then you want to look for functionals, in particular positive functionals, which act on this characters. Okay, and you wanted them to be positive in the sense that when acting on this bulk characters, it's positive. Okay, and acting on the boundary characters is negative. Okay, and you want to also normalize for convenience. You want to normalize these characters acting on the vacuum character. And if it's positive acting on the vacuum character, you normalize to 1, okay, which will not change these properties. And if it acts negatively on the vacuum character, you normalize it to -1. Okay. And with this ingredients, it will give immediately, whenever you construct such a functional, you immediately this inequality which bounds the Brane tension that appear in this equation. Okay, essentially because you have a functional that makes this positive and makes this negative, so it makes this whole thing positive. It will ensure that the functional acting on this piece will be negative or non-positive. Okay, and depending on how it acts on this vacuum character, plus minus, it will give a lower or. Okay. And then it just becomes so whenever you have such functional, it gives a non-trivial bound, and then it just becomes optimization problem, trying to kind of optimize this bounds to get the strongest bounds on the Brane tension. Okay, and there are two ways to proceed. One is the numerical approach, which essentially rely on scanning a space of linear functionals, which are often built out of derivatives essentially in the moduli acting on the characters. Okay, and this is a very general approach. It's rigorous, but the bounds you obtain here is obviously limited by numerical precision. Okay, and I should say there's a very systematic way to carry out this numerical analysis thanks to this SDPP package that was developed by David Summersteffen, that makes possible the numerical part of this in this work. Okay, but there's also a complementary approach. It's analytical. Okay, and this will be based on not scanning some space of linear functional, some kind of very naive space of linear functional, but to come up with very smart positive functionals that satisfy these properties. Okay, and somehow these functionals have this mysterious property that they understand unitarity and crossing. Okay. One thing I should emphasize is that, well, so first of all, these analytic functions are particularly nice in the sense that they give exact results. Okay, because these are exact functionals, so they give very precise proofs for what kind of a boundary is admissible or not. But I should also say that this analytic functions are limited by the fact that they're rather rare. Okay, in particular, at the moment, to satisfy these properties, okay, the only functionals that's known so far, non-trivial function that's known so far, is in the context of one-dimensional bootstrapping problem for the 4-point function. Okay, and that's developed by Dalimil Mazak, and it's also closely related to a functional that's used in the so-called spinless bootstrap, modular bootstrap in the 2D CFT. Okay, so this is one of the key limitations of this analytic approach. Okay, but in this talk, in this work, it turns out that we have to pay very little to we can actually generalize what was developed here to our context, thanks to a relation between a 4-point function and the Annulus spanning function through this map. Okay, this is the conformal map between Annulus and the plane with 2 cuts, which I don't have time to explain. But this essentially, if you think about Annulus as an incarnation of the cylinder, this gives you a 1-to-1 relation between the cylinder spanning function and a certain 4-point function connected by conformal defect in the same CFT. Okay, and with this map, we're able to use the previously developed analytic functional developed by Dalimil in this Annulus bootstrap context, and give rise to precise bounds and precise exact bounds. Okay. Let me skip this technical part and just present the results. Okay. So with this analytic functional, we can prove certain mathematically precise theorems as follows, just to give you a flavor. So one theorem that we prove is that if you study conformal boundaries, or which I often also refer to as just Branes, in the E8 level 1 CFT, So this is the rational conformal field theory as n equal to 8. The boundary conditions for this theory that preserve the maximal Carrel algebra is trivial. There's a single so-called identity brane, essentially because this theory has a trivial modular tensor category and has a single object. With this analytic functional, we can prove exactly that branes, general branes in this theory, which are not classified, okay, and largely unknown, have to have the property that the brane tension is bounded below by 1, and also the boundary operator spectrum has to be bounded above by 1. Okay, and furthermore, the following conclusion will be equivalent, meaning that the equality is satisfied if and only if the boundary gap is also saturated, if and only if the cylinder prime function is precisely determined by the modular J invariant raised to the 1/3 power. And if you know the EA level 1 CFT, this is precisely the vacuum character associated with the EA level 1 CFT. Okay. But emphasize again, this theorem is a theorem that applies to all conformal boundaries of the EA level 1 CFT, okay, for which little is known, but its general conclusion would apply. There's a similar theorem that you can derive using this analytic functional for conformal boundaries of the monster squared CFT. So you can think about it as the holomorphic monster CFT paired with its anti-holomorphic partner. Okay, so it has center charge equal to 24 on both sides. And once again, we proved that the conformal boundary in this theory have found a brane tension that's bounded below by 1. And the boundary operator spectrum has a gap that's bounded above by 2. And once again, the saturation of this bound would happen simultaneously. And at such a saturation, the boundary, the cylinder Pernin function for such a boundary is precisely given by the vacuum character for the monster VOA. Okay. And there's a close connection between the analytic functional that we found and the sphere packing problem in various dimensions. In particular, the functional that we find is precisely the functional that was used to establish rigorously what is the densest packing of spheres in dimension 8 and 24. Okay. Correspondingly by the E8 lattice and by the Leech lattice. I should say that the analytic bounds give very precise theorems, as I mentioned, but they're complementary. What the numerical methods, we also explore numerical methods, and what numerical methods buys us is to explore more bounds in a much larger class, strong bounds in a much larger class of CFTs. Just to illustrate, we get very strong bounds when for branes in this double-zero level models labeled by G level 1. Where G is labeled by this sequence of Lie groups, and if you know about the Lie exceptional series, this is precisely the series that the Lie found. Okay, what's particularly nice about this sequence of RCFTs is that they have at most 2 characters with respect to the maximal Carrel algebra. So they have relatively simple bulk operator spectrum. But once again, it's not known what are the complete set of conformal boundaries in these theories. Okay. In fact, very little is known beyond just the boundaries that preserve the maximal Carrel algebra. Okay. But from numerical methods, okay, in this case, we find strong bounds once again on the brane tension and on the boundary operator spectrum. And we find that for a brane to be stable, okay, meaning that there's no relevant operator in the open string spectrum, the G function coincides with that of the rational identity brane in these theories. Okay, so this leads to a natural conjecture or question that perhaps in these theories, the only stable branes are those related to the rational branes that people already know by fusion with invertible symmetries, which does not change the brane tension. Okay. Finally, let's come to the large C limit of our bootstrap bounds. In this case, a natural target to apply the bootstrap bounds to is pure gravity with an end-of-wall brane, okay, which should be thought of as the bulk dual of some putative boundary conformal field theory, with a large center charge, okay. And this semi-classical solution in the bulk was first explained in nice paper from Takanayagi. The picture you should have in mind is that you have some bulk ADS3, which asymptotically ends on the two-dimensional CFT. And if the two-dimensional CFT has a boundary, this boundary is described in the holographic dual by some end-of-wall brane, okay, which extends into the bulk, on which the ADS3 can also end on, okay. Just to remind ourselves, what's the meaning of pure gravity? Okay, so pure gravity is thought of as the simplest model of quantum gravity in ADS3. It's a conjectured model. It's not proven if it's fully proven if it's not possible. It's not fully proven if this is a consistent at the fully consistent at quantum level, but there's concrete proposal. The idea is that you want to kind of include the minimal amount of stuff in the bulk. Say coming from boundary gravitons and from BTZ black holes, okay, which are boundary gravitons and BTZ black holes, which are no solutions to the Einstein gravity in ADS3. And if such a pure gravity theory were to exist as a quantum theory, its dual CFT must have the following operator, have an operator spectrum of the following type. There's the vacuum, and there's going to be a huge gap. Okay, so just focus on the Virasoro primaries. There's going to be a vacuum, and there's going to be a huge gap, and the gap goes all the way to the so-called BTD threshold, which has dimension roughly C/12. Okay, and then you have a bunch of other you have other BTZ black holes and bound states between, and you have boundary gravitons on top of the BTZ black holes and so on, and possibly other bound states. But it's characterized by this huge gap, okay? And you can generalize this notion of pure gravity in the presence of the end-of-wall brane in a natural way by requiring that in the presence of boundary, the boundary operator spectrum also has a similar huge gap, but now it goes all the way to C/24, which is essentially characterized by the bulk solution involve a BCD black hole, now in the presence of end-of-wall brane, okay? So if you accept this as your assumption on the bulk and boundary gap, which is the notion of pure gravity with end-of-wall brane, you can ask if there are non-trivial bounds on the brane tension from the Annulus bootstrap. Okay, and that should be compared to kind of proposals for the brane tension from the semi-classical analysis. Okay, so the semi-classical analysis from this paper tells you that the brane tension can be any value of the following form. It's proportional to the bulk center charge, and the proportionality constant can essentially be any real number. Okay, so the capital T characterize the brane energy density in the bulk. Okay, not to be confused with the brane that I've been using before, but this is the end-of-wall brane that in the bulk. But one can ask if this is actually fully consistent, and the answer is not. If you study the Annulus bootstrap, you'll find that this number, which seems arbitrary at a semi-classical level, is actually bounded above by some number that's obtained from numerics. It's like 3.3. Okay, so this tells you that with these assumptions on the bulk operator spectrum and the boundary operator spectrum, this semi-classical end-of-wall branes are not consistent. Okay, so you have to give up something. You can give up this kind of boundary operator gap by, as what I guess Yan mentioned sometime towards the beginning of the talk, by including additional degrees freedom to lower the boundary gap. So that will be one way out. Another way out will be to include additional operators also in the bulk. Okay. All right, so I think that's all I'm gonna say, but let me just point out a number of, I'm gonna say about our work, but let me point out some interesting future directions and some open questions. So one already partly mentioned is to study not just the arbitrary boundary states for conformal field theories, but to study supersymmetric boundaries for CFTs in the book that preserve some supersymmetry. For example, to generalize the consideration of D-branes in type 2A or type 2B string theory. In particular, it will be interesting to look for stable non-BPS branes in the context of string theory. Okay, as fast again, these are here by stable I mean the ones that preserving they're stable while preserving into one worldsheet supersymmetry. Okay, such objects will be useful in characterizing the geometry of supersymmetric sigma models. So it's known that even if you consider supersymmetric sigma models with well-known target space, such as Calabi-Yau manifolds or K3 manifold, in this case, the D-branes, the usual stable BPS D-branes will correspond to in a target space picture, branes wrapping holomorphic or more generally calibrated cycles in the target space. But it's known that for general homology class in the target space, there may not be a holomorphic cycle, or in general, there may not be a calibrated cycle. So in that case, it's interesting to ask what will be the stable non-BPS brane in that case. So there's no BPS brane with that homology charge, but one can ask what is the stable non-BPS brane? And such non-BPS brane, their tension of this stable non-BPS brane would be sensitive to the volume of this non-homomorphic cycles. For example, it can determine the minimal volume of such non-homomorphic cycles. And another obvious direction forward is to incorporate additional constraints on boundaries coming from the bulk boundary bootstrap equation, which I already mentioned. And I'm pretty sure this will lead to further non-trivial constraints on the conformal boundaries. And another obvious direction is to incorporate symmetries. Okay, so just to mention one point, that is the boundary states naturally transform under fusion with topological defect lines in your CFT. In particular, the boundary state should form what's called nim wraps for the topological defect lines. Nim means non-integer matrix, okay, just by consistency of the fusion. And by incorporating this structure, it will also hold the promise of additional constraints on the boundary states in the CFTs. I think that's all I'm gonna say. Thank you for your attention, and I'll open now for questions.
Thank you. Thank you for the very nice talk. Other questions from the audience?
Hello.
Yeah.
Yes, we can hear you.
Thank you for the talk. I want to ask, do you know the Bootstrap equation for the supersymmetric boundary? Is that the same as the one for general CFT?
It's not. It's not. So for the supersymmetric one, you have to so in the supersymmetric case, the boundary state has an additional structure that is split into NS. So the Ishibase state have kind of fall into different categories. There's the Ishibase state in the NS sector and the Ishibase state in R sector. So that you'll have, instead of this one bootstrap equation, you get a multiple of this bootstrap equation by also including some topological line that some topological twist that labels the fermionic, includes some fermionic twist lines on this equation. This will lead to kind of additional equations, right?
So that's more promising to be solved, right? Yeah.
So they will give additional constraints on top of this one. That's why you expect to get a stronger constraint, right? And for those, once again, for those bootstrap equations, they have been solved for kind of rational theories like supersymmetric, super conformal Miller models, but in general it's not. Yeah.
Okay, thank you, and looking forward to your paper.
Yeah, thank you.
And I have a question.
Sure.
I guess the G function here. Is I think this G function is like in a some people talk about this localized Tachyons condensation.
Yes, the G function for the open string tachyon condensation can be described by a boundary RG flow, and in that case the G function decreases. This is why people were interested in the G theorem in the old days.
Yes,
the G in the spacetime, in the target spacetime picture, measures the mass of the particle, and and the tachyon open string tachyon condensation tells you how the particle decays essentially.
Okay, but there's also some called like a localized closed tachyon, like you consider like Oberfold.
That's fine. Yeah. So in that case, you just consider Oberfold and similar story, right?
Similar. Okay.
Just the CFT is different, but it's a similar problem. You're still studying how the boundary states change on the RG flow. Of course, there's something else you can consider, which is related to the closed string tachyon condensation. In that case, you want to study a different question, that is how the boundary state change under bulk RG flow, which I have not talked about in this talk. In this talk, always the CFT is fixed, and you're trying to study the boundary states. But you can also ask if the CFT itself changes, say by bulk RG flow, how does the boundary states change? No, that's a separate interesting question.
I see. Okay, thanks. And also, this in your conclusion, you talk about this supersymmetry and deep learning picture. So naively, so if you have an upper bound on this G function, does that mean that there exists some like a maximal volume of this non-holomorphic cycle?
Yeah. Maximal volume for the non-holomorphic cycle to be stable. Yeah.
Okay.
Yeah.
Interesting. Okay, thanks.
Yeah.
I think there's a question in the chat box. There's a question in the chat box.
I see. So in the case of ADS BCFT example, there are definitely more consistent conditions. Yeah, I'm just studying the silliest consistent condition coming from the Annulus bootstrap. In the paper we cited some of the recent works where they study other kind of constraints on the NO world grain, but in the talk I just talk about the simplest. We didn't study the constraints from OP. We only studied the constraints from the Annulus bootstrap in this paper.
More questions? I think I have one more. Maybe I missed some details in this saturation case. You mentioned the E8 level 1. Can you go that slide?
Sure.
E8 level 1 monster square.
Yes.
What are special with those two series? Saturate.
They're just special because they're picked out by this analytic functional. They're also special in the sense that they have a trivial modular tensor category. In the sense that with respect to the maximal Carré algebra, these theories only have one character.
I see. So, naively, I would think that this G equals to 1 can always be saturated for any given theory, because that's just a zero tension brane. And
no,
if you do the folding trick, you do the folding trick for some kind of interface, you always get.
You always have, if you have a topological interface. If you do the folding trick, of course, the double theory would have a boundary that G equals 1. But there are many.
Yes.
Yeah, but there are many places where this goes wrong, right? So first of all, a general CFT is not going to be a double. Second of all, the value of H cap is going to be, it's going to be anywhere. So the non-trivial statements here is that these things are correlated. If G is equal to 1, the gap is also equal to 1. In this case, if G equal to 1, the H gap is equal to 2. I agree with you that if you just look for boundary states which is 1, it's of course easy if your theory is a double, but yeah.
I see. Another thing is since you only constrain you only using this Cardi consistent condition.
Yes.
But in that consistent condition, if you take a large C limit,
yes.
How to understand them more intuitively? Because if you for the second type of consistent condition, you can be more clear. If you take large C limit, it leads to some kind of vacuum block dominance or things like that. But for the first one, if you take large C limit,
yes,
what's going on? Yes, for the
Cardi condition. I think people in the literature would like to. I mean, we didn't do anything. We didn't make any assumption. We just consider literally the bounds and finite C and consider a sequence of C, and we go to large C, like 100 something, and then interpolate.
You mean by numerics?
Okay. Yeah, numerics. Okay. We don't make assumptions, but in practice, when people make these arguments in the context of ADA-CFT, they want to assume some vacuum dominance, which may or may not be true. So yeah, sometimes people take the vacuum contribution from one channel and the vacuum contribution from the other channel, and try to combine in a way, but yeah, that's not what we're doing. But that's something that you could try.
Okay. So the
of course, in the long cylinder limit, the vacuum would dominate here. But in that limit, there's no reason why the vacuum would dominate on the right hand side.
So the last bound is 3.29.
Yeah, it's something like 3.29. Yeah, it's just numerical bound.
What is the special about that value?
Sorry?
I mean, what's the specialty of that value? I mean, if you in terms of
I don't know the special. I don't know anything special about this value. It just come out of numerics. I don't have a deep interpretation.
Yeah. Okay. I mean, if you translate it into the underworld Brane in the ADS3 block, the angles, how much is that angle?
It's just some number. It's the real number.
Okay. I mean, yeah, I want to be more geometric.
Yeah, it's a real number. Yeah, it's a real number. Just the capital T is something that's close to 1, but not so too close to 1.
Oh, close to 1. Okay.
I mean, arctan grows very quickly, right?
Okay. Yeah. Yes.
As T goes to 1, it goes to infinity.
Yes. Yes. So it seems there's still one more question. Oh, okay. Are there more questions? Comments, questions from the students? Yeah, if as you said, if there is a way to get around all these bounds.
Yeah, I mean, there are certainly ways to get
but turning on these fields on the underworld Brane.
Yeah. You can. Yeah. So here I'm just making the strict assumption on the spectrum, and I give you a bound. Of course, there are various ways to get around it. But yeah, so this is
But then then there's a difficulty to understand it, because then there's no more BCFT, but rather a defect or interface CFT. If you view the underworld Brane and the boundary as a whole thing.
What do you mean? I mean, you can just add some fields on the. So here, this is the simplest underworld Brane. you're assuming that you don't add any matter on the brane world volume. You just have some constant tension. This is the Gibbons Hawking term. But you can imagine that you actually need to introduce additional matter and the world brane, and then that will modify.
Yeah. What I'm going to say is, if you do that, then this is not guaranteed to be a BCFT, because this is connected with the original BCFT by interface.
No, it's still a BCFT because as long as you choose the boundary conditions that you choose the matter content such that, and the boundary condition such that you preserve the conformal symmetry, it's still going to be a BCFT from the boundary perspective. Doesn't matter what you do on the end of world brane, as long as it has a boundary condition that's consistent with the boundary conformal symmetry here, that's fine. If you want to have an interface, if you want to describe interface, you want to fill in this picture with the CFT also on this side, ADS on this side as well.
Okay, no, I'm sorry. I'm just viewing this a different way. Just there's BCFT, original BCFT is here, then the brane is here. This is like already an interface.
Yeah, you can think about it, it's an interface between the end of world brane and
that's right.
the 2D CFT. Yeah. So this is sometimes people say as well. In other words, this is what people say. Yeah. This is what people use implicitly in the context of discussing this JT coupled to path. Yeah.
That's right. But it's not really clear if you turning on that CFT on the underworld brane, everything can be again still translated to a bigger BCFT. You know what I mean?
Yeah.
Yeah. Maybe it's not guaranteed to be still a BCFT. Okay, I think there's one more question in the chat box. There's one more question in the chat box.
Yeah, I mean, the question can be generalized to the higher dimension. That's true. But the technique that we use, the Annulus bootstrap, does not have a obvious generalization to higher dimension, as I mentioned, because it uses the two-dimensional specialty of the conformal transformation. But you can still study the other bootstrap equation involving the two-point function of bulk operators. That may give rise to additional constraints on this end of world branes in higher dimensions. Yeah, it is an important question. I agree.
Okay, more questions?
But it's also a bit different in the sense that the problem is harder to define, to kind of make it tractable in higher dimension, because there isn't really a notion of pure gravity in higher dimension anymore. Right. I don't think we believe there's a pure gravity. There's a generalization of pure gravity as a quantum gravity theory in ADS4, for example. Like all the examples that we know that are close to a quantum gravity in ADS4 would also have a higher dimensional, like have an internal manifold, for example, S7 if it's dual to the ABGM theory and so on, unlike the ADS3.
Yeah, I think the question is that Rongxin is maybe interested in ask about any relation of this bound on this entropy or tension to the underworld brane graviton mass, because there's a recent suggestion the underworld brane can localize gravity in higher dimensions.
Yeah. This is known, right? If you The gravity, yeah, you have massive gravity, yeah, effectively on that warp plane, right? That's what happened to the, yeah, the I mean this reinterpretation of the island by people like Karsh and friends, yeah.
Okay, are there more questions? If not, let's thank Yifan for the great talk.
Yep. Thanks for your attention.
Thank you. Thank
Yep.
you very much. It's
Yep.
a beautiful talk.
Okay, have a nice day.
Yeah, we're looking forward to your paper.
Yep.
Thank you, Yifan.
Okay, bye.
Bye-bye.